So if you think about the functions we've looked at so far, moving here into chapter 2, we looked at constant functions, so horizontal lines. We looked at linear functions, which gave us increasing lines or decreasing lines. We looked at quadratic functions. I guess technically here m can't be 0. Which would either give us happy parabolas or sad parabolas. And then we looked at absolute values. But these were piecewise linear, so they were just two lines put together. But if you look here, we've got constants, linear, quadratics. The power on x here is getting bumped up. And so what chapter 2 talks about is they talk about polynomials. And so we're going to be looking at powers of x beyond x squared and what those things look like. And so once again, in other times, this is a nice sort of ice-breaking activity the class will work on together, using a graphing utility to just kind of notice some trends here. And so what we're going to do first is we're going to graph even powers of x. So this first one here, the way this is set up in Desmos is if you type in f of x equals x to the n, it'll bring up a little slider. So we're going to have the slider start at n equals 2. That means that we've got the graph of y equals x squared, and that's our nice friendly parabola. If we bump that up to n equals 4, which it's not doing. Come on. There we go. N equals 4. N equals 6. N equals 8. Okay. There's some commonalities there. So 2, 4, 6, 8. All of them have this basic U shape. And the higher the power, the flatter it gets. Okay, and we can kind of we can see what's going on there with a table. So we can add a table in. Say x1 and f of x1. And we can plug in some values here. Let's do -2, -1, -1/2, 0, 1/2, 1, and 2. So if you notice here, the reason we're getting this U shape is because when you plug in negative values to squared, the negative gets squared away. And that's going to be the same as we bump up the powers here. So anytime you get a negative, if you get a negative to an even power, that's going to give you a positive back. And that's what's creating the U shape. Okay? You plug in positives, you get positives. You plug in negative, you get positives, because a negative to an even power is always a positive. Now let's talk about the flattening that we're seeing here. So let's look at -1/2, for instance. So -1/2 squared is a quarter. -1/2 to the 4th is now 0.0625. To the 6th, to the 8th. And so what's happening there, if we look at the flattening, is if you compare like -1/2 squared to 1/2 to the 4th, over to the 6. You can see that those denominators are getting really, really big, which means that the fractions that come out of it are getting really, really small, and they're really close when you plot them to the x-axis. On the other hand, if I take powers of 2, these things are taken off. You follow? So you can also think of this as the narrowing. Yeah. So things are taking off on the sides. All right. But one thing you want to keep in mind as we move through this chapter, whoops, is the idea that when you have an odd power, you're going to get this characteristic U shape, and the higher the power, the flatter and steeper it gets. Okay? So hopefully that makes sense. Let's take a look at odd powers now. So if we start off with x to the first, that's the first odd power. That's our line that we got. And we can bump this up. Cubed to the 5th and to the 7th. And what do you notice here is, well, if we get beyond the first power there, the 3rd, 5th, and 7th all have this S shape to them. And we can see why there's an S shape looking at the numbers here. Notice that when you take a negative to an odd power, it stays negative. So a negative input gives you a negative output. A negative x gives you a negative y. Positive x gives you a positive y. That causes you to cross through the axis there with an S shape. And once again, we notice the same sort of flattening and steepening because we're looking at the higher powers. And so if you take a negative to an odd power, it stays negative. And so we're going to get this S shape. And it's got the usual flattening and steepening as n gets bigger. Okay, so this is y equals x to the n, where n is odd. And this is y equals x to the n, where n is even. Now you can also play around with the coefficients here. Let's look at let's take this out. Let's take a look at x to the 4th. So there's your characteristic U shape. Let's look at 2x to the 4th. All right, well, there's 2x to the 4th. Pretty much the same shape, just a little bit narrower. If I looked at f of x equals negative 2x to the 4th, you get pretty much the same shape, but now it's opening downwards. And that's the same kind of thing we observed with quadratics. If we had a positive leading coefficient, we got a happy parabola. Negative leading coefficient, we got a sad parabola. If we change this to x cubes, so there's our characteristic S shape. We multiply by 2. It's a little bit steeper. If we multiply by negative 2, instead of being an increasing S, it's now a decreasing S. All right. And hopefully that reminds you of what happened with lines. A positive leading coefficient there with that m. Positive slope was increasing lines, negative slope decreasing lines. Okay, so that was kind of like a little experiment there. You can go through and play with Desmos to get the same results. But pretty much here's the summary, and this is what you're going to want to remember moving through the chapter here. If n is even, okay, so even is going to tell you it's going to be a U shape, and a is positive, so think of a as positive like the positive for the parabola, then the graph of ax to the n looks more or less like a happy U. Right? If n is even, well, once again, that's a U shape, and a is negative, so that means that a is negative, then you're going to get more or less the sad parabola U shape. If n is odd, then that's going to give us an S shape. And if a is positive, think of this as like a positive slope, so it's increasing. You're going to look like an increasing S. If n is odd, once again, that's an S shape. And a is negative, then think of that like a negative slope. That's going to be decreasing. All right? So those are the basic patterns. And these are things you just kind of want to tuck away. Once again, if you know the results about the quadratic functions we talked about and linear functions we talked about, these are just extensions of those to all even and odd powers. All right. So what's a polynomial function? Well, you may have heard, for example, binomial, trinomial. So binomial means two terms. Trinomial means three terms. Polynomial means many terms. And what are the terms? The terms are the things that are being added together. And the terms are going to be all powers of x. So that's what a polynomial is. So this is how they describe it. N here is a whole number. So it's a whole number. These a sub 0, a sub 1, up to a sub n, these are the coefficients of the corresponding powers of x. So what this is trying to communicate is that you've got x to the n, that's your highest power of x, and then the coefficient of that we're going to call a sub n. So it's a notation. A sub n is the coefficient of the nth power. So for example, f of x equals 1 minus 2x minus 4x cubed. If we wanted to write this in the standard decreasing notation, we would have negative 4x cubed plus a negative 2x plus 1. And so in this particular case, the highest power, which is called the degree of the polynomial, is 3. A sub 3 is asking us for the coefficient of x cubed. So a sub 3 here is negative 4. Now you notice there's no x squared. This is asking for the coefficient of x squared. Well, we could be pedantic and say, well, there's 0x squared there. So a sub 2 is 0 because there's no x squared terms. A sub 1 is the coefficient of x to the first power. Oops, that's x to the first. So that's a negative 2. A sub 0 is the constant term, which in this case is 1. constant term you can think loosely of as the coefficient of x to the 0 power. So these subscripts, don't let them put you off. A sub 3 is asking for the coefficient of x cubed. A sub 2 is asking for the coefficient of x squared. A sub 1 is asking for the coefficient of x to the first. And a sub 0, that's the constant term. So we've got some terminology. If you have a polynomial function, and basically we're assuming that the a sub n here is not 0, so that's the highest power of x, the highest non-zero power of x in there. The degree is n. Leading term is the term that has the degree power in it, and the leading coefficient is the coefficient of the leading term. So in this particular scenario, the leading term is negative 4x cubed, because that's got the highest power of x on it. The degree is 3. The leading coefficient is negative 4. So let's practice these definitions here. Find the degree, leading term, and leading coefficient. So degree, once again, that's the highest power of x. In this case, that's a 4. The leading term is the term with the highest power of x, so negative 2x to the 4th. Leading coefficient is the coefficient of the leading term, negative 2. Looking at g of x here, degree, once again, we're looking at the highest power of x, that's 3. The leading term is the term containing the highest power of x. If we write this in with descending order, we can see that the leading term there is a negative x cubed. And what's that leading coefficient? Well, we could write that as negative 1 times x cubed. Leading coefficient's negative 1. Any questions on identifying the degree, the leading term, or the leading coefficient? All right, let's take a look at the next one here. In these next examples, the big difference between these examples and the ones that came before it are these examples aren't multiplied out. So we got to multiply them out. Now remember, when we're asking for degree, leading term, leading coefficient, all we care about is the term containing the highest power of x. So we don't need to multiply everything out. We just need to think about what is going to contribute to the highest power of x. So what you do here is you realize we're going to be multiplying the quantity 2x minus 1 times the quantity x squared plus 3x plus 1. All we care about is the highest power of x that's going to come out of that. So what you do is you take the highest power of x here and multiply by the highest power of x here, and you're going to have a 2x cubed plus something. And the rest of that stuff is going to have powers of x lower than 3. So as far as we're concerned, we don't care about them here. The degree here is going to work out to be 3. The leading term is going to be 2x cubed. Leading coefficient then is 2. So when it's factored like this, you just multiply through the leading terms of each factor to get the leading term of the function. Let's take a look at g of x. Once again, it's factored. We're going to have a negative 2. The highest power in here is x, and that's being what? Cubed. The highest power in here is also x, and that's being what? Squared. And there'll be other stuff, but it'll have lower powers of x. So this would be negative 2x to the what? Well, when you multiply with the same base, you add the exponents. So negative 2x to the fifth. The degree here, highest power of x, is 5. The leading term is negative 2x to the fifth. Leading coefficient is negative 2. All right, let's look at P of z. We've got that negative out front. The highest power of z here is 3z. The highest power of z here is z, but that's being what? Squared. And the highest power in here is z squared on its own. You multiply these together, you're going to get a negative 3z to the 2 plus 2 plus 1, so 3z to the fifth. Once again, plus some other stuff. But we're only interested in the highest power of z, so that would be 5. The leading term is 3z to the fifth. Leading coefficient there, negative 3. And let's take a look at this one. Q of z. Well, once again, we're going to have that 1/2. Now be careful here. The leading term in here is a 2z, and that's getting what? Squared. The leading term in here is z, and that's getting cubed. Now here's where you want to be careful, because not only does that z get squared, the 2 gets squared as well. So this would be 1/2 times 4z squared times z cubed. That'd be 2z to the fifth. So this would be degree 5, leading term 2z to the fifth, leading coefficient 2. Any questions on finding the leading term here when things are factored? The leading term has the highest power of the variable in it. And as we'll see here in a minute, that's going to help us, that's going to tell us something huge about the graph. All right. One of the big concepts we introduce in Chapter 2, that'll be with us through the rest of the course, is the concept of end behavior. So the end behavior of a function describes the behavior of the function at the ends of the x-axis. Now, we know what? On the x-axis has no ends. We imagine the x-axis going off to the left forever, going off to the right forever. And so end behavior is asking us what's happening to a function as x runs off to negative infinity and x runs off to infinity. So, sort of in quotes here, big negatives, like negative 10,000 or 10 million, or big positives. In other words, end behavior is what justifies the use of these arrows here. So we talked about that with x squared. When the parabolas continue to go up as the x's go out. Those arrows indicate end behavior. And so we can see here in this table here, as x goes to negative infinity, the f of x goes to infinity. In other words, the further to the left you go, the further up you go on the y-axis. So the further left you go on the x, the further up you go on the y. And that's accounting for this. As x goes to infinity, as you plug in larger and larger x values, so I'll try to color code this as best I can here. Then notice the f of x is also getting large and large positive numbers, and so we would say that would go to infinity, which accounts for that. So that's the notation we're going to use. We're going to use that arrow notation. So x arrow infinity means you're plugging in larger and larger positive x values. 1,000, a million, a billion. X going to negative infinity, you're plugging in quote-unquote big, meaning big, absolute value big, but very, very small numbers like negative a billion, things like that. Now, if you think about all the even powers of x, all have that basic U shape, and so they're all going to have the same kind of end behavior. Let's take a look at what's going on here with the cubes. So here x is going to negative infinity. And what's happening here to the f of x? It's also going to negative infinity. So the further to the left you go, the further down you go, which accounts for that arrow. Oops, excuse me, this is function g of x here. And if I plug in larger and larger positive numbers as x goes to infinity, the g of x also goes to infinity. So as I move out far to the right, this moves up and accounts for that arrow. So the end behavior for odd function or odd degrees is going to more or less mimic what's happening here with these S shapes. So let's look at a more complicated function. Let's look at x cubed minus 4x plus 1 and try to figure out its end behavior. Oh, my window blasted over there for some reason. There we go. So when we're looking at end behavior, we want to zoom out. So if we zoom out here, notice it kind of wiggles around. But as I zoom out, at least as far as it looks as if as x goes to negative infinity, so as we're moving out far to the left here, it looks like the y values are heading down. So we would say f of x goes to negative infinity. And as x goes to infinity, so as we're moving far to the right, it looks like the y values are heading up. F of x is going to infinity. And so that's how we would describe the end behavior. All right. Any questions on interpreting that? Now, if you think about what's happening here numerically, when x is going to, say, negative infinity, we're plugging in like really big, quote-unquote, negative numbers, like negative 1,000. Let's go through plugging in negative 1,000. You're going to get negative 1,000 cubed minus 4 times negative 1,000 plus 1. Now, that's going to be some incredibly huge negative number. This will be plus 4,000, and this will be plus 1. But this number is so huge, it's going to sort of dwarf what's happening here. You follow? And the same thing if you plug in a positive 1,000. Whatever's happening here is going to totally outpace what's happening here. And so it's this leading term here that's sort of dominating what's happening in this function when I plug in these large numbers. All right, and we can see that numerically and graphically. So what I'm going to do is I'm going to plug in, I'm going to call it L of x for leading term. So in this case, that's x cubed. And let's make a little table here. Whoops. Make a little table here. We'll have x1. We'll have f of x1. And we'll have L of x1. And let's start plugging in numbers here. And hopefully you'll see what I mean. So let's plug in like negative 10, negative 100, negative 1,000. And what do you notice here? So here's your function value at that point, and here's the leading term. So the function gives you negative 959, the leading term gives you negative 1,000. Here, when you plug in negative 100, the function gives you negative 9,999, 599. The leading term gives you negative 1,000,000. So these numbers are getting closer together. Here, this is negative 9.996 times 10 to the 8th. This is negative 1 times 10 to the 9th. These numbers are very close together. All right. If you look at the graphs, look at what's happening when I zoom out. You see how the two graphs are getting very similar to each other? That's because it's the leading term, once again, that's dominating the function as you go off to plus and minus infinity. And so that's the big thing, the big theorem here for end behavior. So the end behavior of polynomial functions is determined by the leading term. All right, and this is huge. This is huge. We're going to use this not only in this chapter, but in chapters yet to come. This is one of those things, since we're dealing with infinity, this is one of those things that gets more formalized in calculus. But for us, if we're given a polynomial, we want to determine end behavior, we look at the leading term. So as an example of this, let's check out negative t to the fourth plus 2t squared plus 1. I think that's it. Minus 1. And we're asked to determine the end behavior. So we're looking at what's going on when the inputs go to plus or minus infinity. All right. Well, here's what we know. As t goes to plus or minus infinity, g of t is going to look a lot like its what? Leading term. And what's the leading term here, folks? Negative t to the fourth. Now, what's important about negative t to the fourth? It's an even exponent, and it's negative. So even means it's going to be a U shape. Negative means it's going to be a sad face U. Okay? So what's that mean? As t runs off to negative infinity, g of t should also go to negative infinity because we're heading down forever. And as t goes to infinity, g of t should also go to negative infinity. Now let's test that out. Let's see if that actually works. Doggo's upset about something. And let's zoom this in here. Okay, so let's zoom in here. So here's our g of t. And as we zoom out, you can see as we go to negative infinity or positive infinity, the graph is heading downward. And we can go a little more with that if we look at the leading term here, L of t, negative t to the fourth. Let's make that a different color there for contrasting reasons. As I zoom out, notice that they look similar to each other. Okay. So it's the highest power, the leading term runs the show as t goes off to plus and minus infinity. So that kind of tells us where the graph is going to enter the picture and leave the picture. Okay, that tells us where we put the arrows on the graph. And so that's called the leading term test. So big concept here. Okay. And the good news is we know what the individual powers of x look like from our investigation at the beginning of class. So here we go. Let's work through these together. Use the leading term test to predict the end behavior of the following functions and check using a graphing utility. So here's a function f of x. What's the leading term, folks? Well, the highest power of x is x cubed. That whole leading term is negative x cubed. So let's think about negative x cubed. It's an odd and it's negative. Odd tells you it's an S shape. Negative tells you it's a decreasing S shape. So it's going to look like this. As x goes to negative infinity, the f of x is going to go to infinity. And as x goes to infinity, the f of x should go to negative infinity. And you can check then on Desmos. I won't go through it because we've already checked a couple of them on Desmos. You see what's going on there. Any questions on how we determine the end behavior of that polynomial function? Let's look at g of x. This is one we are going to do on Desmos because I want to point something out. Leading term here, highest power of x is x to the fourth, 0.01 x to the fourth. So let's take a look at 0.01 x to the fourth. We see that it's an even power. That means it's going to be a U shape, and the leading coefficient is positive. That means it's going to be a happy U. So as x goes to negative infinity, and as x goes to infinity, g of x should both go to infinity. Are there any questions on that? Now, I want to take a look at this one on Desmos in particular, because it kind of shows you why you need to know your math and you can't just always rely on technology. So let's take a look at this one. So let's get back to the standard here. Negative 10 to 10. Negative 10 to 10. And I'm looking at g of t. negative 0.01 t to the fourth. Excuse me, it was plus, wasn't it? It was minus 100. Or was it t's or x's? Oh, it was x's. Forgive me here. Put that in there. X cubed plus 1. So if you graphed it, if you graphed the function on the standard window, this is what you would see. And looking at just this part of it, it looks like our answer is wrong. It looks like as you go to negative infinity, this goes up forever. But as you go to positive infinity, it goes down forever. All right, and that's not what we said. We said that it should look like a U. You follow? Doesn't look like a U, but let's take the time and zoom out. It still doesn't look like a U. And boom. Eventually, it does look like a U. You follow? But how would you know to keep zooming out? I mean, this is nuts. This is like a 10,000? Because you know the mathematics. So the mathematics, the theorem, is going to tell you what to expect. And the technology can help us confirm our answers or suggest answers, but it can't actually prove answers. So I'm going to write that down because that's one of my mantras here. Technology can suggest or verify solutions or answers. But it's the mathematics that proves it. You follow? So that's a lesson that we're going to see again and again and again. We're going to use technology. It'll help suggest answers or help confirm answers. But when it comes to actually doing the work and proving what's happening, we're going to have to rely on the mathematics. So there's a good example of that. All right, these last few, the polynomial is given to us in factored form. And so to get the leading term, we've got a little bit of work to do. So let's review how we do that. H of t equals. Remember, we just go in here and take the highest power from each factor. So we look at the leading term of each factor and multiply them together. T times the opposite of t times t. So negative t cubed. We got an odd exponent and a negative leading coefficient. The odd exponent means it's an S shape. Negative means it's decreasing S. As t goes to negative infinity, h of t is going to go to infinity. As t goes to infinity, h of t will go to negative infinity. P of x, we've got a 3. We've got an x squared times an x squared. That works out to be a 3x to the fourth. Oops, I forgot the leading term is negative t cubed. Leading term here is 3x to the fourth. What's important about 3x to the fourth? The power is even. Leading coefficient is positive. That's going to be a happy U. As x goes to negative infinity, or as x goes to positive infinity, the function's going to go to infinity. Okay? And once again, you can check these on Desmos. Make sure you zoom out far enough. Any questions on these two examples? Okay, P of z. Once again, we need to find that leading term. So we've got the leading term in here is negative z cubed. The leading term here is 2z. Remember, when you take a negative to an odd power, it stays negative. So we'd have a negative 2. Z cubed times z would be z to the 4th. Even means it's a U shape. Negative means it's a sad U shape. So as z goes to negative infinity or positive infinity, p of z is going to go to negative infinity. And our last one here, q of x. You're going to have your 2, you're going to have your x. And then you've got a negative 2x what? Squared. Now remember, you got to square the negative 2 as well as the x. So this is going to be a 2 times an x times a positive 4x squared, which would be an 8x cubed. And what's important about 8x cubed? It's an odd. That means it's an S shape. Positive coefficient means it's an increasing S. As x goes to negative infinity, the q of x will go to negative infinity. As x goes to infinity, the q of x goes to positive infinity. So you get your S shape there. And once again, you're invited to graph these on Desmos to check that out. So when it comes to end behavior, it's the highest degree term that runs the show. All right? So think of it, they're called the leading term because they lead the function as you go off to plus and minus infinity. Any questions on that? Now, these patterns of U shapes and S shapes are going to also help us with what we call local behavior. So end behavior is what's going on at the ends of the x-axis. So what's going on in between? All right. So we've seen polynomials, they kind of wiggle around. And we're going to talk about what drives that behavior. So zeros of polynomial. So you may recall from chapter 1, the zeros of a function are the solutions to the equation f of x equals 0. Geometrically, they're the x-coordinate of the x-intercept. So the zeros of a function are the solutions to the equation f of x equals 0. So we're going to go through a little example. Once again, this is some nice group work usually. So we'll work all together here. All of the functions below have the same zeros. X equals 0, x equals 1, and x equals negative 2. But they have different multiplicities. Okay, so we'll talk about that. Multiplicity is how many times the 0 is repeated. So if I look here, if I set this equal to 0, you'd be setting x equal to 0, x equal to 1, or x equal to negative 2. Those are the three factors there. You set each of those equal to 0. Multiplicity has to do with how many times those solutions come up. So in this case, the multiplicity of each of these is multiplicity 1. Because each of those have the first power on them. So let's run over to Desmos, graph it, and let's observe the shape near these. Let's get Desmos out. Boom. Let's go back to a reasonable window here. And let's look at our function f of x is x times x minus 1 times x plus 2. So here's the zeros, notice. -2, 0, and 1. Note if I zoom in, let's try this. Let's get over here. So if I notice near -2, it kind of looks like a line. Near 0, it looks like a line. And near 1, it looks like a line. Okay? Now it increases through -2, decreases through 0, and increases through 1. But the shape on all of these is a line. Right? Now let's bump up the power on x. So notice everything is the same, except now it's x what? Squared. So when you set this equal to 0, the solution x equals 0 gets counted twice. So the multiplicity here is a 2. These other ones' multiplicities are still 1. So let's go to the graph and let's bump this up to 2. Now notice at -2, if I zoom in at -2, locally that still looks like a line. But look at what's going on at 0. What's that locally look like? It looks locally like a parabola. It's got a U shape. And at 1, looks locally like a line. So, the shape here is a U shape. And these are just lines again. Okay? So notice when that's multiplicity 1, it's looking like a line. When it's multiplicity 2, it's looking like a U shape, like a parabola. Well, look at what we're going to do in these next two examples. Here I'm going to bump up the power here on the x minus 1 to 2. Here I'm bumping it up on the x squared and the 2. So let's look at this together, and hopefully we'll start to see some patterns here. Let's take that off. Bump that up to 2. Notice it still looks like a line at -2. If I zoom in here near 0, looks like a line near 0. But look what's happening here near 1. It looks like a what? A U shape. If I put this on the x and the x plus 2, notice it looks like a U shape near -2 and 0, but near 1 it looks like a what? A line. Okay? So hopefully you see the pattern here. So here we had multiplicity 1, 2, and 1. We had a line, we had a U shape, and a line. Here we have multiplicity 2, 1, 2. Here we had a U shape, line, U shape. And now let's go down to the bottom here and look at degree 3. So degree 3, degree 1, degree 2. Let's see what happens there. Maybe you have a guess. So degree 3, degree 1, degree 2. So here x negative 2 looks like a U shape there. 0 when x is 0. What kind of shape is that? It's an S shape. And at 1, we've got the line again. So we've got multiplicity 3 looks like an S shape. Multiplicity 1 looks like a line. Multiplicity 2 looks like a U shape. Hopefully this is ringing some bells here from what we did first part. So what's going to happen here? X equals 0, that's got a multiplicity of 4. That's a multiplicity 1, and that's a multiplicity 3. So what do you think is going to happen near 0? U shape near 1. Line, and near negative 2, S shape. So those powers of x that we talked about at the beginning of the period, those are affecting the shapes near the x-intercepts here. So let's test that out. So we've got 4, 1, and 3 there. So let's look at that on Desmos. So we'll make that a 4, a 1, and a 3. I might need to zoom out a little bit to capture all the action. Here we can see here at negative 2. Negative 2 is a solution coming in at 3 times, so it looks like the S there. Here at 0, 0 is coming in x to the 4th, that's 4 times. So that's a flatter U shape. And then at 1, we're looking at a line again. Okay? So once again, to tie this all together, if you set that equal to 0, you got x to the 4th equals 0, x minus 1 is 0, x plus 2 cubed is 0. So we get x equals 0 here, but we get that 4 times. That's that multiplicity there they're talking about. X equals 1, we just get that 1 time. And here we get x equals negative 2, but we get it 3 times. All right. S shape, U shape, linear. Driven by those powers. All right. So those powers also govern the local behavior. And so we've got the following, and once again, this result really goes back to what we started talking about at the beginning of class with how the powers look. So if x equals c is a 0 with multiplicity 1, the graph of y equals f of x is linear near C0. If we've got even multiplicity, it's U-shaped. And if it's odd multiplicity bigger than 1, then it's S-shaped. And once again, those match those basic power functions we talked about at the beginning here about an hour ago. All right? So, let's put all of this knowledge together to help us graph this function by hand. All right? We'll graph it by hand, and then we'll use Desmos to confirm what we do. So, here's the strategy. First thing we're going to do is find the leading term to help us figure out the end behavior. That's going to tell us where the graph is coming into the picture and where it's leaving the picture. Then we're going to find the zeros and state the multiplicities. That's going to tell us where it's going to cross the x-axis, or where it's going to touch the x-axis, and then the shape around it. Then we'll find the y-intercept. We'll put it all together. And then we'll make a sign diagram. Using our homemade graph, we'll make a sign diagram. And we'll check everything on Desmos. All right. So this is putting it all together. So if you can follow this example, then you're in good shape. So let me recopy this polynomial to make sure I get all the bits and bobs here. So p of x is negative x plus 1 squared times x minus 2 times x squared plus 1. Let me just double check. Yeah, there it is. Okay, so leading term. To get the leading term, all I care about is the highest degree term. I don't need to multiply the whole thing out. I just got to multiply out the highest powers in each. So I've got that negative. I don't want to forget about that. Looking in the first factor here, I've got an x, and that's being what? Squared. The second factor, I've got an x to the first power, so just x, and then I've got an x squared. Multiplying that all together, add those exponents, we get a negative x to the fifth. So what do I know about negative x to the fifth? What's important about that? The exponent is odd, and it's negative, so that means we have a decreasing s. So this means as x goes to negative infinity, goes far to the left, the p of x is going to go to positive infinity. And as x goes to infinity, p of x goes to negative infinity. The further left you go, the further up we go. The further right we go, the further down we go. So what that tells us about our function here is that our graph is going to start up here in the second quadrant, do some stuff, and then it's going to leave in the fourth quadrant. Okay, so it tells us where to start and end our graph. Now, to get the zeros, we set p of x equal to 0. And we split it into the factors. So either x plus 1 squared is 0, or x minus 2 is 0, or x squared plus 1 is 0. Here we're going to get x equals negative 1. And how many times does that come up? Twice. So this is going to be multiplicity 2. Here we're going to get x equals 2. How many times does that come up? Well, just once. So this is going to be multiplicity 1. And when you try to solve x squared plus 1 is 0, well, let's just think about it for a minute. You get x squared is negative 1, I guess. Can you get a real number whose squares to negative 1? No. No matter what number you plug in for x, you're going to square it. You're going to get 0 or bigger. If you add 1 to it, you can never get back to 0. So we get no real solutions here. All right. But let's take a look at our graph. So we know that we got one of our x-intercepts here at negative 1. So negative 1, 0 is one of the x-intercepts. And we know that 2, 0 is another x-intercept. Okay, we got that by setting the function equal to 0. Now, what's it going to look like at negative 1? Since it's multiplicity 2 it has to look like a U shape. So since it has to look like a U shape, what's going to happen here is the graph's going to come in, and instead of crossing through, it's just going to bounce. So multiplicity 2 means you've got a U shape. Multiplicity 1 means it looks like a line. So it's going to bounce up here at -1. It's got to cross through the y-axis somewhere. We'll find that out in a minute. It's got to turn around at some point, and then it's got to head through like a line at 2. And where can we figure out where it crosses the y-axis? Well, that's where we can find p of 0. So when I plug 0 in, 0 plus 1 is 1, squared, 0 minus 2, 0 squared plus 1. P of 0 is 2. So there's the y-intercept. So you see how this all stacked together, folks? The end behavior tells us how we're going to start the graph and finish it. The zeros tell us where it's going to hit the x-axis. The multiplicity tells us if it's going to rebound at the x-axis or pass through the x-axis. And the y-intercept tells us where it's going to hit the y-axis. You put all that together, you got a pretty decent graph. What would our sign diagram look like? Let's sneak that in here. We'll put down -1 and 2. You got to put the zeros there. It's above the x-axis, positive. It's still above the x-axis, and then it's what? Below the x-axis. Any questions on putting all that together? So we've got global behavior, zooming out, end behavior. End behavior is determined by the leading term. Odd powers are S shapes, even powers are U shapes. Locally at the zeros, we've got the same thing happening. Odd powers, well, we could have lines if it's first power. More generally, higher order odd powers are S shapes, and then even powers are U shapes. Let's see what Desmos has. This is our rough sketch. Didn't take us that long. Let's confirm our answer with Desmos. We've got a negative x plus 1 quantity squared, x minus 2 times x squared plus 1. Let's check out Desmos's graph. So there's the intercept, intercept, intercept. Now, what our graph doesn't give us, that Desmos does, is it doesn't give us the name of this, the top of the hill here. This is something we could find algebraically if we knew a little bit of calculus. All right. This point up here is called a relative maximum. All right, so we talked about the maximum and minimum of a graph. A relative maximum you can think of as, loosely speaking, the relative maximum is like the top of the hill. This function has no maximum. But locally, if I zoomed in, it does. So it's got a local maximum value of 10.2 something, at the x value 1.43 something. So that's a local maximum. So top of the hill. Here in this polynomial, there's no minimum because the y values head to negative infinity. but it has what we would call a local minimum at negative 1, 0. Okay? Because if you zoom in, that's the bottom of the valley there. So polynomials are going to have these local maxes and mins. And they'll be important depending on the situation. Unless the local max or min happens at an intercept, we're not going to be able to find them algebraically. We'll have to use Desmos to help us with points like this. But what's nice about the polynomial theory that we have now is if I got the leading term and I have the zeros and the multiplicities, I'll know where to expect the local maxes and mins. What do I mean by that? I know that based on my graph, this has to go up. I know to expect a local max somewhere between negative 1 and 2. You follow? So the math we do will help us when we have to refine it using the technology later.